A formal charge is associated with any atom that does not exhibit the appropriate number of valence electrons. And when it is present, a formal charge must be shown on the Lewis dot structure. So to be correct, we have to include the formal charge. Formal charge calculated takes the number of valence electrons that are assigned to that atom from the periodic table. And remember, you find that just by where it lives on the periodic table as its group number. And you subtract the assigned electrons to that element in the compound, all right? So group number minus assigned electrons. Let's kind of review what I mean by assigned electrons. All lone pairs and half of the bonded pairs are assigned to an atom in a structure. So let's take, for example, a compound with the central atom carbon. Let me draw it bigger. Here's the central atom carbon leading up to an oxygen that has 3 sets of pairs. And then these carbons are leading out to hydrogen. Do you find any formal charge? Well, one of the tricks I like to use is to take a circle and encompass each atom, bisecting every bond. And when you do so, inside of that circle, you will find all of the assigned electrons. Everything encircled is now assigned to that particular atom. Focus your attention on the oxygen. Oxygen lives in group 6A, so it has 6 valence electrons. How many circles, or how many electrons inside the circle? Well, I have 1, 2, 3, 4, 5, 6, and half of that bonded pair. So there are 7 assigned electrons, giving it a formal charge of -1. And notice how they're showing that as part of the actual dot structure in that answer. The formal charge of negative is placed right on the oxygen's elemental symbol in this compound. And it happens to be the only atom with a formal charge. Take a look at the carbon in the center. Carbon lives in group 4A, so it has 4 valence electrons. There are 1, 2, 3, 4 assigned electrons. Remember, each half of a bonded pair, meaning it has a 0 formal charge. Each of the hydrogens have 1 assigned electron, 1 electron inside of its circle. Hydrogen lives in group 1A, so it has 1 valence electron minus the 1 that's assigned, giving it a value of 0. So the one and only one atom with a formal charge in that example structure is the oxygen, and it was determined to be a -1. We can try a couple more from your homework. This one's asking, what's the formal charge? See how I'm abbreviating formal charge on the nitrogen. So as you draw that structure, draw a circle around the element that bisects each bond, because that's the way that we can assign 1/2 of a bonded pair to each element, so that the other electron then gets assigned for each of the hydrogens. So here we have N in the circle. Nitrogen lives in group 5A. It has 5 valence electrons. The number of assigned electrons are those that are encompassed inside that circle, which is 4. So nitrogen has a +1 formal charge and would need to be shown in the structure written as a +1 next to the elemental symbol for N. How about another? Find any formal charges in these examples. So I'm doing some homework problems. The first one, AlH4. I'm going to draw a circle around the aluminum, and inside that circle we can see that aluminum has 4 assigned electrons. Aluminum lives in group 3, so it has 3 valence electrons. But there are 4 electrons in the structure that it's assigned, so its formal charge is a -1. Let's find the oxygen in the second example. Draw a circle around its structure, and we have 1, 2, 3, 4, 5 assigned electrons. Oxygen lives in group 6A, so 6 valence electrons are what it would like to have. But right now it's assigned 5, giving it a +1 formal charge. And here I can see that nitrogen, who lives in group 5A, so 5 valence electrons, and inside this circle there's 1, 2, 3, 4, 5, 6 dots, 6 assigned electrons, making it have a -1 formal charge. Going the opposite way, I wanted to try some examples like this as well. Draw the structures and make sure that you can place the formal charge where it belongs. So let's model that with letter A, BH4 -1. Boron lives in group 3A, so it will contribute 3 electrons. Hydrogen lives in group 1, but there's 4 of them, so that's 4 total electrons. And the -1 charge means you have 1 additional electron. Adding electrons makes the species negative. So the total number of dots here is 3 plus 4 is 7, plus 1 more is 8 dots. Pick the least electronegative element, and that would be boron. Never pick hydrogens. Attach back all single bonds to that central atom. That used up 2, 4, 6, 8 electrons. So we're out of electrons. And notice that boron, who lives in group 3A, therefore has 3 valence electrons, has 4 electrons assigned to it, and that's where you see the -1 as the formal charge now on the boron. Let's try another, make it easier. NH2 negative. Nitrogen lives in group 5A, so it will contribute 5 dots to this structure. Hydrogen lives in group 1A, so it will contribute 1, but there's 2 of them, so that's a total of 2. And then the -1 charge means we get an extra electron. So 5, 6, 7, 8 electrons again here. We'll place the nitrogen and connect back both of the hydrogens, and that used up 4 dots to do so, leaving us 4 to place on the central atom. Notice that hydrogen does not get any dots. It only has 1 bond and it's done. So now nitrogen, who lives in group 5A, has 1, 2, 3, 4, 5, 6 electrons assigned to it, making its charge a -1. And the last one, C2H5 with a +1. Of course, we get the carbons connected together. We use the hydrogens to complete the valence shell, but notice that we're left 1 hydrogen short, 1 deficient, to create the octet on that second carbon. So therefore, that's why we see the +1 assigned to it as a formal charge. It is electron deficient, knowing that carbon would like to have 4 bonds, but that particular carbon only has 3, making it a plus overall. Carbon lives in group 4A. It has just 3 assigned electrons next to it, making its formal charge a +1. I wanted to share a few of those exceptions and kind of look at section 4.3, exceptions to the octet rule. Well, most of the common elements are going to follow the octet rule. You know, hydrogen is a notable exception, and we've mentioned it all along, because hydrogen only wants to become like helium. Hydrogen will only have a 1 bond requirement, no dots. So technically it doesn't have an octet. It has a duet of a duet is 2 electrons, and then it becomes like helium. So since it has a duet instead of an octet, it breaks the octet rule. The other one I wanted to mention and already have earlier is boron. Since boron lives in group 3A, underneath boron is aluminum, but aluminum is a metal, so we know that metals will form ions. Boron is a metalloid and therefore will form covalent bonds. But since it only has a 3 bond requirement, it will break the octet rule. Boron, with its 3 valence bonds, has 3 bonds and 0 lone pairs. And that's okay, based on the number of bonds around it matching its group number. So this will be an octet rule breaker, but it's okay because of its group location. Sometimes elements in the 3rd row, and I just mean by the 3rd row is period 3 on the periodic table, they have empty d orbitals that are available to accept electrons. It allows them to expand their octet. So, octet, there I got it. Row 3 would include elements like phosphorus, sulfur, chlorine even, but phosphor and sulfur are very good at accepting more than their share of electrons around that octet. If I look at the phosphorus electron configuration, 1s2, 2s2, 2p6, notice now I'm into the 3rd energy level, 3s2, 3p3. The 3rd energy level does have d orbitals. We know that it has d orbitals, but they're unoccupied for the phosphorus element. But they're available to expand the octet. So when I think about where those electrons come from, I mean, this is the atom of phosphorus. How in the world can I get more than 8 electrons? Because here's this 2s, that's full. Here's the 3p3. I can see that there's 3 electrons there. It only looks like there's 3 open spots for bonding. And that's verified when I draw the electron dot configuration for phosphorus. There's only 3 open spots for bonding. But as an occasional rule breaker, phosphorus does have these open, unoccupied orbitals that it can use to put electrons in if it's asked to. It doesn't want to, but if it's asked nicely, it can expand its octet. Here's phosphorus in the center atom. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I look at all of those electrons around there, you can see 5 bonds, which really represents 10 total electrons. That's definitely breaking the octet rule. And how it does so is by placing some of these electrons in the unoccupied d sublevel. They're open and available for bonding when needed. Sulfur can do the same thing. Notice around the sulfur atom, and this is just kind of looking at sulfur, I see that it only wants to form 2 bonds. It's got 6 dots. But if it's made to, it can form up to 12 electrons, which is 6 bonds around the sulfur atom, because it has open d orbitals. Now remember, period 2 has no d sublevels. When I write a configuration 1s2, there's no d sublevels. Period 1 will never be able to expand its octet. Whoops, and in the 2nd energy level, we said that we had a 2s2, 2p6. That's it. Since there's no d sublevel, before we reach the 3rd energy level, there's no chance that a 2nd row element can ever break the octet rule. So it will never break octet. That was an N. In other words, it won't have more than 8. So when I say break the octet rule for more than 8 electrons. Now, because boron clearly broke the octet rule, but it was not going over 8, it was going under 8. It had 6. By the time it formed 3 bonds, only 6 valence electrons. So it doesn't break the rule, but what I'm referring to is period 2 has no ability to expand and go over 8 electrons. It has to be a period 3 element or greater to be able to even do this. And really, we're not going to focus too much on rule breakers. We're more focused on just saying that it happens, and if it does happen, it's because it has D sublevels. Glyphosate is the compound widely used in weed killer and is the active ingredient in Roundup. Add lone pairs and all the nitrogens and oxygens to complete the octet, part A. Okay, so we're good at that. We know nitrogen, who lives in group 5A, wants 1 set of lone electrons and 3 bonds. Oxygen, who lives in group 6A, 2 sets of dots, 2 bonds. So I can complete the dots on oxygen and making sure that it has 2 bonds, 2 dots. I can do that very quickly on each oxygen, making sure I set 2 dots. We got it. 2 sets of dots for each oxygen. Do that for the nitrogen. Here's one. 2 sets of dots, 3 bonds, it's perfect. We added all the lone pairs on the N and the O. Done. Letter B. How many electrons surround phosphorus in the given structure? Well, here's phosphorus, and I'm going to just encircle all of the electrons around the atom. How many bonds? 1, 2, 3, 4, 5 bonds. Well, that's the same as saying 10 electron. 10 bonds is 5 shared pairs. And that's a total of 10 electrons. There's 10. That's a rule breaker, isn't it? Which atoms in this compound do not follow the octet rule? Well, clearly that's the phosphorus. That's the skill level of recognizing rule breakers. Boron, he's a rule breaker with only 3 bonds. Hydrogen, he's a rule breaker, only 1 bond. Recognize that phosphorus or sulfur or other larger atoms have the ability to break the octet rule. You don't have to predict when, but if you see it, just know that it's okay. It's acceptable because they have their empty d orbitals to expand and allow more bonding around the central atom. When we consider resonance structures, these resonance structures are 2 equally valid Lewis dot structures that have the same arrangement of atoms, but a different arrangement of electrons. Same arrangement of atoms. The atoms are connected in the same way. But the different arrangement of electrons. So the bonds between atoms may be different. Let's give you an example of one. Here is a polyatomic ion called the bicarbonate ion, hydrogen carbonate or bicarbonate. Now remember, because it's an ion, we may see that some of these bond rules are not being followed, and that's why it's carrying a charge. So here I have kind of carbon attached to all of those atoms there, and I know that I've got to do single bonds. I have, let's see, hydrogen who's going to contribute 1, oxygen will contribute 6. There's 3 oxygens there all together, and a carbon So here we have, oh, and don't forget the -1 means you get one extra electron. So the -1 charge means we get to add an extra electron. So that's 18, 19, 24 dots. And when we did this, we did 1, 2, 3, 4, 5, 6, 7, 8. That leaves us 6 dots remaining. Golly, 1, 2, 3, 4, 5, 6. Oh, that's too many dots there, huh? How about... All right, so we're drawing this bicarbonate polyatomic ion, HCO3 negative. I've placed single bonds between all the atoms and tallied up that that used 8, leaving us 16 dots. And I'm just going to place the 2 dot requirement around each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Leaving me 4 dots remaining, and that's 4 dots to kind of make sure that I get a double bond to one of these oxygens and maybe another set of lone pairs to the other. And that creates the -1 charge on the oxygen. Now let me repeat why I didn't put double bonds here, and I'm just going to draw something wrong and then tell you why it's wrong. A moment ago I said I had 2 sets of dots, and I had this already staring at me, and I put 1 bond here leading up to this oxygen. Well, why didn't I just put a bond here instead of another set of dots? And what I want you to examine is what that did to the carbon. That's a rule breaker right there. See how too many bonds on the carbon? And so that's not allowed. Carbon will never, ever have more than 4 bonds, and I just gave it 5 bonds there. So that's not going to happen. So what I just did is give oxygen a set of dots and made it a -1 charge. I put a set of double bonds up and a single bond to make sure that I had 4 bonds only on the carbon, knowing that when I have a -1 charge, like we do on this polyatomic ion, the oxygen may be upset with its 2 bond, 2 dots requirement. It's okay, but carbon will never have more than 4 bonds. But you know, an equally valid choice? Equally valid in the sense that I could have placed the double bond leading out to the oxygen from the far right and a single bond leading up to this oxygen, and put the -1 charge up on the oxygen up high. These are 2 valid structures for this polyatomic ion called bicarbonate. I did a resonance structure. We will separate resonance structures with a double-headed arrow, saying one possible correct structure for this bicarbonate is to place a double bond to the oxygen going up and a single bond left or right. But another lovely choice is that I could have placed the double bond going to the oxygen to the right and the single bond up. 2 equally valid structures are called 2 resonance structures, where I'm given a choice of where to place the double bond between 2 equal choices. Now you notice the atoms are connected in the same order. H, then O, then C double bond O, C single bond O. They're same connectivity, but I'm just moving the location of the double bond and moving a set of lone pair electrons. I'm allowed to move electrons. I'm not allowed to move atoms. So which one is correct? Well, the answer is actually both of them are correct. When I had a carbon double bonded to oxygen, single bonded in this direction, and I said that this is a perfectly valid choice, and that this is an equally valid choice, where the HOC leads up to the single bond, and then this over here has the double bond, They're equally valid choices, two resonance structures. I want you to think of the true bond as being a hybrid of both structures, that these electrons are actually delocalized and spread apart evenly between all atoms involved in the bond. So if I were to redraw and give you a better picture of what's happening, the bond between the two oxygens is not really a true double, not really a true single bond, but it's delocalized, spending time evenly between the oxygen up high and the oxygen to the right. Do you see what I'm trying to draw there? Let me just clean it up and try to emphasize. From carbon to both oxygens have a delocalized double bond, and I'm going to draw dashed lines to let you know that it's not really a double bond in this direction single. It's not really a single and then a double in this direction, but that shared pair of electrons is being spread evenly, spread out, delocalized across multiple atoms of the same size. So it's got a larger region of space that it's spending time with. That the true shared pair are going equally between the up top and the to the right oxygen at the same time. A delocalized electron set. This actually is a very stabilized occurrence. The molecule gains a great bit of stability by being able to delocalize its electron pairs. So neither structure is actually true, but more of a hybrid of both structures. It's just, think about blending two structures. Did you know that a nectarine is a mix of a peach and a pear? I don't know if that's true. But it's not like a hybrid fruit spends time being one fruit and then the other. If a nectarine is a blend of a peach and a pear, it is not. I don't know what I'm saying. But a hybrid fruit like a nectarine doesn't go back and forth to being a peach and then a pear and then a peach and then a pear. It's a blend of the two structures, a hybrid. That's exactly what this molecule is. It's both pictures at the same time. When you mix red and blue, when you mix blue and yellow, what do you get? Is that green? It's not that green is a hybrid, or it's sometimes blue and sometimes yellow, but it's a hybrid of both. That's what a resonance structure is. So as we're considering delocalizing a double bond, remember, we're allowed to move electrons, but not atoms. So if we examine this structure, the carbon leading out to the hydrogens, leading out to a carbon double bonded to an oxygen, bring your eyes to this section of the molecule first. Carbon has two valid choices of where to place the double bond. It could place the double bond leading to the up top oxygen, or an equally valid choice is placing it to the right and making that the double bond. Oops, that's 3 dots. These two are known as resonance structures. We've delocalized the double bond. It spends time equally between both oxygens on that carbon. Examine letter B. Notice if you bring your eyes to where you see the double bond, because resonance will always involve a double bond. We cannot form a double bond on hydrogen, but we can form a resonance structure with the nitrogen next door. We would have hydrogen attached to carbon, and then instead of a double bond going up to the oxygen, we would place a single bond. And then the double bond could be delocalized between the nitrogen and the carbon. So another valid resonance structure is to distribute the double bond in the opposite direction from the carbon. Knowing that a resonance structure actually is a hybrid of both, that the oxygen carbon bond and the nitrogen carbon bond truly have a delocalized electron pair being shared between both atoms. And we represent that in two resonance structures separated by a double-headed arrow. Those are resonance structures of our compound. A very stabilizing effect. Label each pair of compounds as resonance structures or not resonance structures. Remember the two rules here. You're allowed to move electrons, which are bonds. You're allowed to move bonds in electrons, but not allowed to move atoms. So one of the first things to note is, do the atoms, are they attached in the same way? I have a nitrogen, carbon, oxygen. Nitrogen, carbon, oxygen. Perfect. I'm not breaking the atom rule. Then I'm just checking to see if those two are resonance structures. All I've done is moved a set of electrons, and that's clearly what's happened. This set of electrons became a bond, and that's separated. So yes, these are resonance. The letter B, this looks funny to me. Notice here the oxygen is part of a structure in the bone, it's attached between the two carbons. And now all of a sudden the oxygen has moved a completely different location. So this is not a resonance structure. You cannot move atoms, only bonds and electrons. I see that happening down in this example as well. The carbon and the nitrogen have exchanged places. I can't do that and have a resonance structure. I'm not allowed to move atoms. So these are not resonance structures. Let's see here. Carbon, carbon, NH, carbon, carbon, NH. This has the same atoms, right? Same connectivity. So therefore, all I did was move electrons. That's certainly the case. It looks like a set of electrons went to make a double bond. The double bond became a set of dots, and that's what separates these, are moving electrons. Same connectivity, different sets of attachments of bonds. So yeah, this is a resonance structure separated by a double-headed arrow. Let's draw 3 resonance structures for the polyatomic ion called carbonate. Remember carbonate from last chapter? CO3 carrying a 2 negative charge. That means we get 2 extra electrons. Carbon has 4 valence electrons, lives in group 4A. Oxygen with its 6 valence electrons. And then the negative 2 charge says, hey, we get 2 more electrons to contribute to our structure. That's 24 total dots. Carbon in the center, attach back all 3 oxygens and retally. 1, 2, 3, 4, 5, 6. That's 18 more dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18 dots. We're done. Except carbon doesn't have the 4 bonds it needs. So we need a multiple bond to satisfy the carbon. We need a double bond. So what do? Do we take it from this oxygen? Do we take it from this oxygen? And do we take it from this oxygen? And the answer is absolutely yes. That's our 3 structures. Do you notice that we have 3 equal choices to create a double bond? Choice number 1. let's put a double bond between the carbon that's lying to the left I know that it's upsetting the oxygen's 2 bond 2 dots, but that's why it's carrying a charge. It's got 2 oxygens that are upset, but that's one equal valid choice for an ion carrying a charge. When it's charged, it's going to break its normal oxygen rule where we want 2 bonds, two sets of dots. The -2 charge says there's 2 oxygens in there not performing that way. But why did I go there when I could have equally drawn a structure in this direction, single bonds to either side? That's another very valid choice. That's a second resonance structure. And do you see the next choice? Oh yeah, the carbon double bond could have been leading out to the right, and all of those dots up here and over here, creating a third equal resonance structure. Now remember, it's a hybrid. It's not really any of them. It's a hybrid of all of them at the same time. That when I stand at the carbon and I look out at all oxygens, they're all equal distance away because I have 3 oxygens that are delocalizing an electron pair. Delocalized means it's not really spending time only between the carbon and oxygen to the left. It's not really just spending time between the carbon and the oxygen on top or the carbon to the oxygen to the right, but it's spending time equally in all directions. Delocalized bond sharing. That's what resonance is all about, a delocalized sharing of electron pairs. With carbonate, we had 3 equal choices because the oxygens in all 3 directions provided 3 choices of where to go.